96. While studying the phenomena of fluorescence and phosphorescence, Becquerel came across a mineral which shone in bright sunlight. But when the weather became cloudy, its fluorescence ceased. As the weather remained cloudy, he wrapped the mineral sample in black paper, put the contents in a closed desk, and forgot about it. Incidentally, the mineral happened to be placed over a Maltese cross, which was kept over a light-proof box of unexposed photographic film. Some days later, when Becquerel took the mineral out, he noticed that the photographic film appeared fogged. Becquerel reasoned that the material emitted fluorescence even in absence of sunlight. When the photographic film was developed, Becquerel found that the film was fogged with an image of the Maltese cross. This is how the photographic film looked after it was developed. Becquerel assumed that the fogging of the film was due to some rays emitted from the mineral compound, which could penetrate through the black paper and the silver cross and expose onto the photographic film. On further studies, it was found that the mineral Becquerel used in his experiment contained uranium salts, and that uranium emitted radiation constantly without any excitation or charge by an external source. Later studies and experiments based on these observations conclusively proved that this was a nuclear phenomenon known as radioactivity exhibited by some elements having unstable nuclei. Unstable nuclei can attain stability by emitting particles. A nuclear phenomenon in which an unstable nucleus undergoes decay is called radioactive decay. In nature, a radioactive nucleus can decay by three modes, namely the alpha decay, the beta decay, and the gamma decay. In alpha decay, a radioactive nucleus emits a helium nucleus, which is referred to as an alpha particle. In beta decay, a radioactive nucleus emits either an electron or a positron. A positron is a positively charged particle with mass same as that of an electron and magnitude of charge also exactly same as that on an electron. If an unstable nucleus releases an electron along with an antineutrino, it undergoes a beta minus decay. If it releases a positron along with a neutrino, it undergoes a beta plus decay. In gamma decay, the radioactive nucleus emits high-energy photon. A detailed study of alpha decay, beta decay, and gamma decay will be taken up later. Let us first derive a relation for the rate of radioactive decay. For this, let us consider a sample of a radioactive element containing n number of radioactive atoms at time t. The number of nuclei, Dn, which will decay, will be proportional to n, since the more the n value, more will decay in the time interval dt. The number of nuclei that will decay will also be proportional to the time interval dt. If we take a longer dt into consideration, then more nuclei will decay in this longer interval dt, since longer the interval, greater the chance of decaying. Thus, dn will be proportional to n dt. Or we can say dn will be equal to minus lambda n dt. Here, lambda is a constant of proportionality and is called the decay constant or disintegration constant. negative sign shows decay of nuclei. This implies that dN by dt is equal to minus lambda n. Let this be equation 1. This can also be written as dN by n is equal to minus lambda dt. Let this be equation 2. Integrating equation 2, we get integral dN by n in the limits n naught to n is equal to minus lambda integral dt in the limits t naught to t. Here, n naught is the initial number of nuclei at time t naught, and n is the number of nuclei at a later time t. Evaluating the integral, we get log n to the base e minus log n naught to the base e is equal to minus lambda t minus t naught. If we take the initial time t naught as 0, we get log n by n naught to the base e is equal to minus lambda t. This can also be written as n is equal to n naught e to the power of minus lambda t. This equation is called the law of radioactive decay. Let this be equation 3. In general, we are interested in the number of nuclei decaying per unit time than the number of nuclei present in the sample. Number of nuclei decaying per unit time is known as the decay rate and is denoted by R. R is equal to minus dN by dt. Let this be equation 4. Decay rate R is also called the activity A of the sample. Substituting equation 3 in the equation 4, we get R is equal to minus d by dt of n naught into e power minus lambda t. Simplifying further, we get R is equal to lambda n naught e power minus lambda t. Let this be equation 5. Substituting equation 3 in equation 5, we get R is equal to lambda n. Now, at time t is equal to 0, let R be equal to R naught. Then, R naught can be written as R naught is equal to lambda into n naught. Substituting R naught in the place of lambda n naught in equation 5, we get R is equal to R naught e power minus lambda t. This is another form of the law of radioactive decay. Let this be equation 6. The SI unit for decay rate R is becquerel, denoted by BQ as shown. 1 becquerel is equal to 1 decay per second. Another unit of R is curie, denoted by Ci as shown. 1 curie is equal to 3.7 into 10 power 10 becquerel. The period of time taken by a substance undergoing decay to decrease by half is known as half-life period. It is the time interval for which both N and R are reduced to half of their initial values. Half-life period is denoted by T half. From equation 6, we have R is equal to R naught into e power minus lambda t. Substituting R equal to R naught by 2 and T equal to T half in equation 6 and solving, we get T half is equal to log 2 to the base e by lambda. Substituting the value of log 2, we get T half is equal to 0.693 by lambda. Let this be equation 7. Another measure of estimating the time for which a radioactive nuclei lasts is the mean life or average life, denoted by tau. It is the average time a substance exists in a specified form. It is the time interval in which N and R reduces to 1 by E of its original value. Let us now substitute R equal to R naught by E and T equal to tau in equation 6. We get R naught by E is equal to R naught into E power minus lambda tau. On simplifying, we get tau is equal to 1 by lambda. It shows that mean life tau is the reciprocal of the disintegration constant. Now, T half is equal to 0.693 tau. It is important to note that these relations for half-life and mean life are statistical in nature. They cannot predict the exact behavior of each and every nucleus in the radioactive sample considered. Rather, they only predict the total numbers. For example, consider a sample of 100 atoms of radioactive nuclide of half-life 20 hours. Since the half-life is 20 hours, we can say that 50 atoms of the radioactive sample would decay in 20 hours. But we cannot predict exactly which particular 50 atoms of the sample would decay. Experiments have proved that even though the sample contains all similar nuclei, under identical conditions, all of them may not decay simultaneously. Thus, it is impossible to predict when a particular nucleus will decay. However, prediction can be made about how many of these nuclei will decay in the small interval of time dt. Therefore, the equations developed for radioactive decay will work only when n is large.